Glad you're back. Let's go ahead and start applying some of these stress transformation equations to solve an example problem. We're going to start with a simple example problem. So just going to start with stresses acting on a block, and now we want to find the stresses at some arbitrary angle. In this case, it's been defined 65 degrees rotated from the horizontal plane. Go ahead, give it a try, plug into the equations, and you'll get the answers.
In this example problem, they're asking us to calculate the normal stress and shear stress acting on the plane AB. And we see that AB is rotated from the XY orientation that we are viewing this element. So I like to begin the problem by first identifying the stresses I have on the system in my current XY coordinate. So sigma x, if I look in the x direction, my normal stress in the x direction, I don't have any normal stress applied. So sigma x in this case would be 0. In the y direction, I have a compression force of 12 ksi applied. So we know that compression is negative, and so I'll assign sigma y to be a negative 12 ksi. Lastly, we have to consider our shear stress, tau xy. And so if I look at the right-hand side of this block, I see that I am on the positive x plane, but that shear stress is moving in the negative y direction. Therefore, it's negative 10 ksi. You can also go back to the sign convention that we adopted. We had a positive sign convention when we derived all of the stress transformation equations and when we labeled all the stresses on these blocks. So you can go back to that, and if you just want to have that picture in your mind, whenever shear stress looks like what we have on this element, it's negative, and then if it's opposite of what we have here, it would be positive. Now the question is asking for the normal stress and shear stress along this plane AB. So I sketched the little shaded block in there in my picture, and now I want to enlarge that block. Not sure that enlarging is a word, maybe just enlarge that block. Alright, so again I'm going to include my original XY coordinate system. And now on the rotated system, I want to have my x prime and y prime axis. And I can see that if I was to rotate my x-axis up to that dashed line, I would have to rotate 65 degrees counterclockwise. And so that will be our value for theta. Theta will be 65 degrees in this case. Now the question is asking for the normal stress to AB, and so that is perpendicular to AB. So what is the stress value that's perpendicular to AB? Hopefully you realize that the perpendicular stress to AB, or the normal stress to AB, is sigma y prime. And then the shear stress along plane AB will be tau x prime y prime. So this is really the hardest part about the example problem. Once we get to this stage and we now know that the question is asking us to solve for sigma y prime and tau x prime y prime, all we have to do is use the stress transformation equations that we previously developed, and we just have to plug in the values that we identified already for sigma x, sigma y, and tau xy. Now I know this problem is a little bit simplistic, but this is kind of like the final step in a typical engineering design. So we would have done all of the stress analysis, and we'll be doing more of that throughout the rest of the semester. And then we would eventually, from that stress analysis, be able to draw this block that we see at the top right hand of the screen. And then we are going to go from that to start answering some of the questions about stress at that point. Now, as we plug our values into this sigma y prime equation, I just want to caution you that we have to be careful with our algebra. So we have signs on our stresses, and we want to make sure those signs get substituted correctly into the formula. And so, like we see, we have 0 plus the negative 12 over 2 minus quantity of 0 minus a minus 12, so that minus minus will become plus. So I know it's just algebra. I don't want to, worry you too much. It's just going to be algebra, but make sure that you're plugging in the signs from the stresses that we identified in the first step to solving this problem. So I'll go ahead and write this out so that you can make sure, and I would encourage you to go ahead and do this math yourself as well. Make sure you're understanding where these different numbers come from. But we see that sigma y prime will be negative 6 minus 6 cosine 130 degrees plus 10 sine 130 degrees. So that means sigma y prime will come out to be 5.517 KSI. This is going to be normal to the plane AB. I always include a direction with my stresses or forces. So I like to kind of show this as a direction. And so I'll just sketch my direction here. I could be more complete even if I included the angle of rotation there up to plane AB. All right, the question also asked us to identify the shear stress tau x prime y prime on this rotated plane. So we're going to go ahead and copy the tau x prime y prime equation, and then we're just going to substitute the values again in making sure that we keep track of our signs. So I'll leave you to it. You can follow along with the rest of this video. You'll see the calculations work out. We see that tau x prime y prime will result in a positive 1.832 KSI, and this means that the shear is acting on the positive y prime plane in the positive x prime direction.
Good job. We did it. We got to the right answers. Use the formulas. Hopefully you found the formulas pretty easy to apply, right? The formulas are a little long, maybe a little hard to remember, but pretty easy to apply. Just make sure you watch your signs as you plug in positives and negatives into the equation. Make sure you do all your algebra with those positive and negative signs. Otherwise, you'll be in good shape. Go ahead, check out the next video. We'll solve another example.